Hello class. Today we're going to go through section 11.1. The good news is there's no assignment yet today. We'll be looking at 11.2 and completing that before we give any assignment at all. So this will be a fairly short lecture today with no assignment. So enjoy that break while we have it. Chapter 11 is looking at designed experiments. And we're looking at an analysis of variance, AOV, analysis of variance, which is why it's also called an ANOVA test. An ANOVA is an analysis of variance. It's looking at how much these two different sets or multiple sets vary, all right? Basically, this is a type of hypothesis test for 3 or more populations. The P didn't get written off there. So far, we've always been testing 2 populations, but this is a type of test, an ANOVA, for 3 or more populations, okay? Before we go into that type of test specifically, we would also like here in 11.1 to look at some general concepts, basic concepts for experimental design. So this is kind of switching gears from what I just introduced. This basically is for all of chapter 11. We're now looking at a very specific part, that's 11.1. Up until now, we've considered only 2 ways of collecting and comparing the data. We've been using independent random samples. That's what we've used the majority of the time. We also looked at paired data, where we matched up before and after type of situations. Often the data was collected as a result of some type of experiment to systematically study how 1 or more factors are influenced by the variable being studied. Okay, so now we're going to look at 2 types of ways of collecting data for an experiment. The 2 types of experiments that we're talking about are designed versus observational. So 2 different types of an experiment. In a designed experiment, the first one, the analysis determines the treatments, the methods of assigning units to treatments. Usually the experimenter sets up a control group that does not receive a treatment or some variable, and an experimental group that does receive some treatment. Maybe the easiest way to understand this would be, let's say we're testing a drug. We would break up the people that are going to be considered for this experiment into 2 groups. One group would get the drug, the other group would get just some type of placebo. We're very intentional about assigning one group the experimental drug. The other group gets a type of placebo. They're referred to as the control group. They would not get the drug. We would then look at the results of how the drug affected the experimental group, but did not affect the control group. That's a designed experiment. Some key parts. If you're running a designed experiment, you control who gets the variable or the drug and who does not. Very important difference with a designed. The second type was the observational. Remembered on this previous slide, we had design one type, observational the other. Well, on an observational experiment, the analysis just observes treatments. The analysis does not determine who gets the treatment. This would be more like if somebody decided to take a drug versus people that did not. Maybe, for example, a smoking type of drug. People that smoke chose to smoke on their own. We did not assign them having to smoke. We observe the results of smoking over 5 years, 10 years, or 40 years. That's what's obviously been shown to cause cancer. But that would be an example of an observation. We do not force one group to get a certain treatment, get a drug, or whatever the treatment might be. We just observe people that have or have not gotten that variable. Many experiments are a mix of the designed and an experimental. Some examples. A chemistry professor goes to Randy Van Persum and charts the number of hours logged in the academic support program by the chemistry students over the entire semester. The professor then determines the mean number, the average number of academic support hours utilized per student in the chemistry program. Is this observational? Is it a designed, or is it a mix? Well, in this particular case, the chemistry professor did not predetermine who gets the academic support. The professor just went and observed who went in and got it. Consequently, this one would have been observational. A math professor desires to know if developing a time concept strategy would be helpful for students while taking a test. The professor asked one of the sections of applied stats to read the entire test over the first 10 minutes and not be allowed to write anything down. They would then use the normal remaining 40 minutes only to complete the test. The other section of stats would come in at the normal time and take the test as usual over the entire 50 minutes. The professor would do this for the first test, and then on the second test, the professor would ask the other section to read for the first 10 minutes. In other words, switching it around. After taking the first two tests, the professor would compare the mean test score from each section. Is this observational, designed, or a mix? Well, hopefully pretty obvious to you that it's a designed experiment. The professor is controlling who gets the treatment. In this case, the treatment is they're forced to read the test all over the first 10 minutes, not starting, but just reading or summarizing the test. That's a type of variable, a type of treatment. The professor controlled which section got the treatment, hence it was designed. The person running the test is in control of who gets the treatment and who does not. Another example. The Student Affairs Committee decided to perform an experiment to determine if students would study more with particular incentives. They decided to provide free ice cream in the library for different amounts of time, ranging from 1 to 2 to 3 hours every first and third Thursday of the month, beginning at 6 p.m. They also decided to provide free popcorn in the library, ranging from 1 to 2 to 3 hours every second and fourth Thursday of the month, beginning at 6. The committee would then poll the student body to determine if the students felt their amount of study time in the library had increased due to these enticements. Is this an observational, designed, or a mix? Well, by now you know I've covered the first two. This one is likely to be the mix. It's a mix because we are very intentional about giving free ice cream on the first and third Thursday. We're very intentional about giving free popcorn on the second and fourth Thursday. We're determining when that variable is given out. We're also determining how much of the variable is given out. That's a design part. But we're not controlling who comes there on a given Thursday or a given Tuesday. That is partly observational. So this is a type of mix of the two. I'm going to come back to that one here in a moment. Some terms that you should be familiar with. Response variable. It's the variable of interest we're trying to measure. It's called the dependent variable, oftentimes used as y. Well, in this example, think to yourself, what would be the dependent variable? You can pause and read it a few times if you want. But because of time, I'm going to go to the dependent variable. The dependent variable we're trying to find, does the amount of study time increase? So the response variable is the amount of study time. Did that change because of these enticements? Response variable, amount of study time. The factors can be quantitative or qualitative. These are variables that we're looking to see if they have an effect on the response variable. Remember, the response variable was the study time in the library. We're looking what variables might have affected that. Well, the variables here would have been the free ice cream or the free popcorn. Those would have been the variables. The levels are the amounts of these factors that we're putting out there. So the levels are giving different degree of the factors. For example, the levels would have been 1 hour, 2 hours, and 3 hours, because I might have ice cream for 1 hour, ice cream for 2 hours, ice cream for 3 hours, or I might have free popcorn 1 hour, free popcorn, etc. Those hours were the levels. So then the treatments are the combination of the factor level. For example, free ice cream for 1 hour, free ice cream for 2 hours, free ice cream for 3 hours, free popcorn for 1 hour, free popcorn for 2 hours, free popcorn for 3 hours. Those would have been the 6 different treatments. All of them are the different combinations that we could put out there. The experimental unit is the object that we're looking to see if it's changing. In our case, the experimental unit is each individual student. Pretty straightforward and easy, I think, for the most part. In both types, there is strict control over the factors contributing to the experiment. The values combined with the levels are called the treatments, and we talked about that. The object is to compare and estimate the effects of these treatments. That's what a designed experiment is going to do. I'm going to start now looking at a type of hypothesis test here for this completely randomized design. It's achieved when the samples of an experimental units chosen for each treatment are random and independent of each other. The design is used to compare treatment of 1 or 2 or multiple means. We're really focusing on multiple means here. We've done their designed experiments for 1 or 2 means in the past chapters. This is something that you need to be aware of. Put a star by this in your notes. When I'm comparing multiple means, that would mean 3 or more. My null and alternative are easy. They are always this. For example, if I had 3 means, I would start off by saying the null is mean 1 equals mean 2, which equals mean 3. If I had 4 of them, it would be mu1 equals mu2 equals mu3 equals mu4. 5 of them would go up to 5. K of them would go up to K. We start off assuming they're all equal. We're hoping to provide evidence that at least 2 of them differ. At least 2 of them are not equal, one being obviously bigger than another. But I want to emphasize again the word always here. When I'm looking at 3 or more means, not proportions now, but means, 3 or more means, these are always my null and alternative. We'll come back to that in our next lesson. When I'm looking at 3 or more means, the test is going to be done by comparing the difference between the means to the amount of sampling variability. That means how much they're spread out. It's also like saying the size of the standard deviation of each group. This is something different now. When I'm doing 3 or more means, we use a test statistic F, not a Z, not a T, but a new test statistic that we're throwing out here. F is for multiple means. Again, not multiple proportions, but multiple means. It is calculated using a ratio, that means like a fraction. So this F is going to be found by evaluating a fraction. That's not so unusual because you remember Z was also a fraction. Z was x minus mu divided by the standard deviation. That was a fraction. And the difference, even when I had 2 populations, it was a fraction, as was the T. So ratio is not so much of a new concept, but because I'm looking at 3 or more populations, that's why we're using an F. A layman's definition of an F: we measure the variability between the means. This would be the means of each sample. We divide it by the measure of variability within each group. That's referring to the standard deviations within the group. Another way of saying it is we're going to be summing the difference between all the means. Differences, that would be like the first mean minus the second, first minus the third, second minus the third. That's if we had 3. And we're summing the standard deviations. Again, this helps you if you can follow along. It's kind of a tough concept, I get that. But it helps you understand how the F measures the variability. To give you another understanding of that, I'm going to take an example here. Suppose I were to take a random sample of 7 football players and look at their mean GPA and found it to be 2.8. Suppose I were also to take a random sample of 6 students who went on a spring service project and found their mean to be 2.5. And finally, suppose I were to take a random sample of 5 students who were one of the choirs and found their mean to be 2.44. First of all, I'm not trying to make any assumptions on football players, choir, or people that do spring service projects. I'm just putting this out there for an example. So I've got the mean of the football players, 7 of them, to be 2.8. The mean of the spring service projects to be 2.5. The mean of the choir members to be 2.44. This would lead us to suspect or believe that the average football player would have a higher GPA than the average person who went on a spring service project. That would also lead us to suspect it would be higher than the mean GPA of the choir members. But are these differences from evidence that would be statistically significant? Are they different enough that I have mathematical evidence to say the football players are higher than the other 2? To answer that question, I must consider 2 components. I need the size of the difference. That would mean the difference between 2.8 and 2.5, or 2.8 and 2.4. That would be the size of the difference. And I also need to look at how much variability are within the football players, are within the spring service project people, or within the choir members. Considering the following possible samples, I'm going to now take 2 different sets of made-up samples to give you an idea. Okay? Here's the first set. I put the football players in red, spring service project in green, 5 choir members in blue. So these are individual football player GPAs that I made up. These are individual spring service project GPAs that I made up. These are individual choir members. Notice the football player has the 2.8 average. That's the average of all of those, so I made them up accordingly. Standard deviation, 0.6. Here, I found the average of these spring service to be 2.5. And again, I'm hoping that you see that these 2.8, 2.5, right here, 2.8, 2.5, the last one is 2.44 with those standard deviations. This is the average of all of the individual students, 2.6. Okay? This particular one is quite spread out. Notice the standard deviation is 0.6, 0.5, 0.5. Now I've made up a new set. Look how much smaller the standard deviations are. 0.2 instead of 0.6, 0.12 instead of 0.52, 0.05 instead of 0.5. Same overall means. But these are just tighter together. How does that affect my F statistic? Well, here's a visual of that. The red are the football players. Here's a GPA of 1, GPA of 2, GPA of 3, GPA of 4. This was the first set of data. These were the red football players. The green were the service project, and the blue are the choir members. The overall mean was 2.6. That's, again, the average of all of them. Because these were spread out, there's quite a bit of variance between the bottom football player and the top, between the bottom spring service project and the top spring service project, between the bottom choir member and the bottom. They were quite spread out. Gave me an F of 0.7. Compare that now to this group right here. I'm going to have to fold this up a little bit. This group of football players is tighter. They're almost all between 2.4 and 3.1, where these went down into the 1s and up into the mid-3s. These football players are bunched together. The spring service projects are closer together than the other one. The choir members are much bunched together. Same means, but just bunched together. This F value was 9.673. The further away from F equal to 1, the further these F values are from 1, the more evidence we have that there's a difference between the groups. I need to say that again. The further the F value is away from 1, we're always comparing it to 1. The further it is from 1, the more evidence we have, the more statistically significant the evidence is that there's a difference between football players, spring service projects, and choir members. This set of data would give us very strong evidence that the football players have a higher GPA. This set of data up here, because the F was close to 1, this set of data would have had insufficient evidence to indicate the football players were ahead of the other players. That's a visual of what the F looks like. This is kind of a tough concept, I get that. Next, we're going to look at some tables. You don't necessarily need to copy this down. It'll show up in your textbook, oftentimes in some computer printouts. The degrees of freedom for these, because we quite often have small samples. The degrees of freedom are always two components. They're actually usually an ordered pair. The ordered pair for the degrees of freedom is a k minus 1 and an n minus k. The chart for our F statistic has two different variables, k minus 1 across one side and across the top, and n minus k. K refers to the number of groups. In the previous example, I had football players, spring service project, and choir members. There was 3 groups, so K would have been 3. N refers to the total number of data points. So it would have been 7 scores from football plus 6 from spring service plus 5. We would have had 18 scores. N would have been 18. So 18 minus 3 would have given me 15. K minus 1, there were 3 groups, minus 1 would have been 2. So in that previous example, the degrees of freedom would have been the ordered pair 215. These two refer to the difference between the treatments, means, and the variation ones, the errors. Added together, they give you SS total. These two are always added up to get the total. So if they give you a total in one of these, you can get the other by subtracting. They give you these two, you can get the third by adding, but they're added up. This is the numerator. We talked about the F being a ratio. This is our numerator. Notice it's right there, MST. Here's my F. This value is my denominator. So notice this SST over the K minus 1 gives me the overall numerator. SSE over the N minus K gives me the overall denominator. That's a lot of complications there. Don't panic on this. These numbers will be given on a computer printout because they are very nasty to compute. We could do it, but it would take a lot of time. But you should remember, this divided by this gives me the numerator of F. This divided by this gives me the denominator of F. That part you should have down. As I mentioned before, the F statistic is a ratio. It's the numerator, MST, divided by the denominator, with, again, this ordered pair of degrees of freedom. Values of F close to 1 suggest the means do not differ. To make sure that you catch that, I have to go back here once, see if I can find that. I'm apologizing here. Here's the one I wanted to get back to. Do you remember that I said if we have 3 or more means, this is always my null and my alternative? Well, that means if my F value is close to 1, we're saying they do not differ. Another way of saying that, if F is close to 1, I have insufficient evidence, and I got to continue to assume they're all equal. But if my F value gets further away from 1, we're going to have lines in the sand again. If it goes over that line in the sand, gets further away from 1, maybe F is 3, or F is 4, or F is 8, or F is 10. The further it gets away from 1, it means that I have evidence to reject that they're all equal, and I would now conclude the alternative that they differ. That's how that's going to be used. When we're running one of these designed experiments, this would be, for example, if you're doing some type of project or a research paper or a thesis or something like that, these are conditions that you have to have out there. We need randomness of design and independence. They have to have normality, the populations. We need to at least have us believe that they are normal populations with relatively equal variance. We create the ANOVA summary table. That ANOVA summary table was what we just had a moment ago. I not find that? It's one of those I told that you should be able to add up two of them to get the third. That's the table I'm referring to. I did find it here. You have to create that ANOVA summary table. That's this table right here, ANOVA summary table. A lot of times they'll give you that or these parts of it in a computer printout. I talked about having sufficient or non-sufficient. Conditions required, this would be if you're running this on your own someday and for a thesis or something or a dissertation, you have to have independent random samples. All the samples need to be from normal distributions. The standard deviations or the variances need to be approximately equal. When we come back for our next lesson, we're going to take a bunch of examples where we run these types of ANOVA tests. For right now, I just wanted to introduce it because to do all of it in one lecture would have been about an hour and 45 minutes, which would be too long. So we have an easy one today, no assignment, and we'll see you on Wednesday for our next lecture.